Hello, this is Farhan Shakil from the Republic 2.0, and today I've come up with a past paper of Unit 2 from Edexcel International WPH12. The specifications of this paper include waves and electricity, so we'll be talking about all the multiple choices and the structural problems in this paper. So first of all, we've got this question number 1. The refractive index of the vegetable oil is 1.47, and if the refractive index of the vegetable oil is 1.47, you need to calculate the speed of light in meters per second. So first of all, we're going to use the formula that N is equal to C upon V. And if N is equal to C upon V, what does that mean? That we need to calculate the speed of light in the particular medium. So it would be C upon N, and that comes out to be 3 times 10 raised to the power of 8 divided by 1.47. We just need to divide them up, and after division, we'll get the final answer as the B, 2.04 times 10 raised to the power of 8. Now, in the question number 2, a ray of light is incident on the boundary between the perspex and the air. The angle of incidence is greater than the critical angle of the perspex air boundary. Which of the following statements is correct for the perspex air boundary? So, we all need to know that whenever the angle of incidence is greater than the critical angle, that is a required condition for the total internal reflection. And if that is the required condition for the total internal reflection, what is meant to happen that all the light should be reflected back into the first medium, right? Then you have got this question number 3, which is the following units is equivalent to the coulombs. So if I'm talking about the equivalent units of coulomb, we have got something like that, charge is equal to I times T, or from another formula, voltage is also equals to work done upon charge, meaning thereby Q should be equal to work done upon volts. So from this formula, the unit of charge comes out to be ampere seconds. But from this formula, the unit of charge comes out to be joules per watt. So which formula we're going to go ahead with? And that has to be the B1, because ampere per second is not the unit, but ampere second is, right? Then you've got this question number 4. A student set up an apparatus shown something like this. When the string is plucked, it vibrates with a frequency f. Which of the following single changes would increase f? So first of all, we just need to know the formula for the speed of wave in a strings, and that is v is equals to the square root of t upon mu. And if you remember, the formula for the velocity was f lambda is equals to t upon mu, and you will be left out with the frequency to be 1 upon lambda root of t upon mu, right? Once we have got this formula, everybody knows that the wavelength in a string can be expressed in the form of length, right? We've done this much derivations in the chapter. So that must be n times L, number of loops times L, root of t upon mu. So you can see that frequency and length are inversely proportional to each other. Frequency and tension are directly proportional to each other. And similarly, the frequency and the mass per unit length are inversely proportional to each other. In this case, you're going to increase the f. So L should decrease, T should increase, and mu should decrease as well. Mass per unit length should decrease as well. Now, if you look into the options, decreasing the length, so that does make sense, right? If you're going to decrease the length, the frequency should increase. So that is why I'm going to go with the option number A, right? Next, I've got this energy levels, right? Energy level diagram for the hydrogen atom is shown. And you have got the arrows A, B, C, and D shows 4 possible electron transitions. Which transition would result in the emission of a photon with the shortest wavelength, right? Shortest wavelength, what does that mean? That since energy is hc upon lambda, shortest wavelength means the maximum energy. And we can get the maximum energy whenever an electron would jump from the from the highest energy level to the lowest energy level. So you can see that 0 is the highest energy level, minus 13.6 the lowest energy level. So only in this transition, the photon emitted by the light would have the maximum energy. So that is why the transition would shortest wavelength would be A, right? Because it has the highest energy gap. Now we have got this circuit, and in the circuit, we have got a negative thermal coefficient thermistor. What does the negative temperature coefficient thermistor means? Remember that it means that with the increase in temperature, the resistance of such a circuit or such a component should decrease, right? So the temperature of the thermistor is increased. You are increasing the temperature of the thermistor. What does that mean? that the resistance of this component should decrease, right? So we need to talk about the readings in the ammeter and the voltmeter. If the resistance is decreasing, what does that mean? That the total resistance of the circuit is decreasing. If the total resistance is decreasing, opposition to the current is decreasing. So the current should increase, right? So the ammeter would show a higher reading. Is that clear? And then we have got the voltmeter, right? So, everybody knows that V is proportional to R. So if R is somehow decreasing, the voltage should decrease as well. So what does that mean? That the reading across the voltmeter is meant to decrease. So that is why I'm going to go with the option number D, right? And then I've got this question. We have got two waves of wavelength 2 meter. We've got the wavelength that is 2 meter are produced by a source at point X, and they're superposing each other at the point Y, right? And if they're superposing at the point Y, what does that mean? First of all, we need to calculate the phase difference, right? The formula for the phase difference everybody needs to know is 2 pi upon lambda times the path difference, right? This is the formula that we should be using. Now, if you talk about this formula, you can see that the path difference of these two waves is, the total path covered by this type of a wave is 8 meters, and the total path covered by the wave along this direction has to be 9 meters. So the path difference would comes out to be 9 minus 8, meaning thereby 1 meter. So I'm just going to plug this value over here, and I've got 2 pi upon the wavelength. The wavelength was given in the question, and that was 2 meters. I'm going to plug it down over here, times the path difference, and that was 1. 2 cancels out by 2, and you've got just pi radians. So that is why I'm going to go with the option number D. Now, similarly, I've got this question number 8. I've got the energy stored by the solar powered lamp, and that is 6 kilojoules. And then I've got the EMF of the battery, and that is 1.5 volts. And I'm going to calculate that which of the following is the charge that passes through the lamp. So everybody knows that the voltage is work done upon the charge. And if you're calculating the charge, it has to be work done, which is 6 times 10 raised to the power of 3 joules, divided by the voltage, which is 1.5. And whenever you're going to divide them up, you'll be having 4,000 coulombs of charge. That is why I'm going to go with the option number C. And then I've got this question number 9. When the monochromatic light is incident on the surface of a metal, photoelectrons are emitted. Which of the following statements is correct? Well, whenever you talk about the photoelectric effect, remember that the conclusion of this topic, even from the book, was that energy of the photons, whenever you're talking about the energy, that depends upon the frequency, not the intensity. And if somebody is really emphasizing you to talk about the intensity, so remember that the number of photons emitted is proportional to the intensity of light. Remember these two relationships, and you'll be done with the photoelectric effect. So I'll read out the statements. The maximum kinetic energy of photoelectrons depends upon the intensity of the incident light. Well, that is not the case. The number of photoelectrons emitted per second, well, that is not the case, because he's considering a relationship between the number of photons and the frequency. The maximum kinetic energy of the photoelectron depends upon the frequency of the incident light. That does make sense, right? So I'm going to go with option number C, not D as well. Then I've got the two wires X and Y, which are made up of the same material. The wires are connected in series. The current in the wire is I, as shown. Wire X has twice the diameter of the wire Y. Which formula they are talking about? I is equal to NAVE, right? So what does that mean? That drift velocity, this V, is inversely proportional to the area, right? So since you can easily see that wire X has twice the diameter of the wire Y, right? So what does that mean? It has twice the diameter of the wire Y. The mean drift velocity of electron X is V, right? Which of the following is the mean drift velocity of the electron in Y? You can see that the area of Y is less than area of X, right? So it would be having a higher drift velocity, right? It would be having a higher drift velocity. So you cannot go with 0.25, you cannot go with 0.5. Either 2 or 4 is going to be the right answer. But if you think about the formula is pi d square upon 4 for the area, right? So if you're doubling the diameter, the original thingy would replace by a factor of 4. That is why the drift velocity of the wire Y, since it has a low area, should be 2 square, yani 4v. So that is why I'm going to go with the option number D. Now we have got these questions. We're going to talk about the structural problems now, and we're going to start with the question number 11, right? In the question number 11, the wire has a resistance of 65 milliohms, the length is given, and the resistivity is given. And we need to calculate the diameter of the wire, right? So I'm just going to use the formula R is equals to rho L upon A, which can also be written as rho L divided by pi d square upon 4, and I'll be left out with 4 rho L divided by pi d square, right? Since I'm calculating the diameter, the d square has to be 4 rho L divided by pi times R. I'm going to calculate the plug in the formula. I'm just going to plug in all the values in the formula. 4 times the resistivity, which is 5.6 times 10 raised to the power of negative 8, times the length. The length is to be 0.25 divided by 3.14 times the resistance, which is 65 times 10 raised to the power of negative 3. I'm going to calculate all that answer, and then I'm going to take the square root, and the final diameter that I would be having, you can also have it by using the calculator, and that has to be 5.2 times 10 raised to the power of negative 4 meters. That is how I'm going to calculate the diameter over here. In the next question, you've got this question number 12. A student uses a ray box to direct a narrow ray of light onto the surface of the glass block, right? On the surface of the glass block, as shown, you've got an air glass boundary. Calculate the angle of incidence. Now remember that what is going to be the angle of incidence? You just need to draw a normal line over here, and this is going to be the angle of incidence, right? And if you want to measure the angle of incidence, you need to use a D over here. So the angle of incidence, in my regard, it would be something like, it looks like something like 40. So that the angle of incidence must be somewhere around 50 degrees. Remember that it is just an estimate. We just need to use a ray box to determine the angle of incidence. So I'm going to write my estimate, and that has to be 50 degrees. Now, I need to calculate the angle of refraction in the glass block. So I'm just going to use the Snell's law, where n was equals to sine of angle of incidence divided by sine of angle of refraction. So from this formula, sine of angle of refraction would be equal to sine of angle of incidence divided by the n. Sine of angle of incidence has to be 50 degrees, and n has to be 1.5. You're just going to divide them up, take the sine inverse, and the refraction angle that you must be having would be something like 32 degrees, right? So that is how I'm going to calculate the angle of refraction. Remember that if I'm having 50 degrees over here, you can have a different angle over here as well when you're going to measure it accurately, right? But I'm just taking an estimate, so that is 50 degrees. But remember that, the angle of refraction after plugging these values should come out to be 32 degrees, okay? You could have a different angle of refraction as well, depending upon the estimate that you're taking, but that should be an appropriate estimate, right? Now, in the B part, the light from the ray box is unpolarized. When reflected by glass, some of this light will become polarized. Explain the difference between the unpolarized light and the polarized light. We need to talk about the difference between the unpolarized light and the polarized light. So remember that, this is a theoretical question. Remember that whenever you're talking about the unpolarized light, in an unpolarized light, particles would be having oscillations or vibration in many different planes, right? Whenever you're talking about those particles would have oscillations in many planes, right? And whenever you're talking about the polarized light, remember that the particles or the photons of such light would have oscillation, they would have oscillation only in one single plane, that is perpendicular, to the direction of light, right? Even whatever direction the light is going. So this is a 3-marker question. You just need to write, these differences. If you've got anyone else, you can write that as well. But these two differences are fine. Now the student uses a polarizing filter to view the light reflected by the glass block. Explain what she would observe as she rotates the filter. So remember that whenever you're talking about the reflections of the light, it is governed by the formula I is equals to I naught cos square theta, if I'm not wrong, right? So you can see that the intensity would vary as you're gonna change the theta or the angle of orientation of the filter. Did you get that? And remember that, so in this case, by using this formula, intensity is going to vary, right? And if any one of you is doing maths as well, he must know that we must have a maximum to a minimum value, because cos 0 is 1 and cos 90 is 0. So as we approaches 90, we'll have a maximum to minimum variation, right? And after 90 degrees, it would start increasing again up till 180. Okay. So these are the 3 points that we need to mention, because what she would observe the difference in the intensity as you're going to rotate the filter. As you're going to change the theta, she would have a difference in these values. After these things, we've got this question number 13 now. So concrete is often used in building constructions. It may develop cracks. Everybody knows that. Ultrasounds can be used to find these cracks. The transducer send pulses of ultrasound into a pieces of concrete as shown, something like this. You're going to bombard some ultrasound and you'll be able to identify the crack wherever it is. The transducer detect pulses of ultrasound reflected from the crack. To be detected, the reflected pulse must not overlap with the pulse emitted by the transducer. You've got the V over here and you've got the temperature, because the speed of the ultrasonic waves should change with respect to the temperature. Now we've got this case, and in this case, the pulse of ultrasound is incident on a crack in this piece of concrete. The crack is at a distance of 4 centimeters from the transducer, right? The crack is at a distance of 4 centimeters from the transducer. We just need to talk about that whether the waves should be moving this much distance or more than this distance. The temperature is 23 degrees Celsius. If you have got the temperature, you must have the speed as well. And if I'm talking about 23, this is 21, 22, 23. So at 23, the speed is going to be something like 41, let it be 20, right? 4120 meters per second. So you've got the speed, and that is 4120 meters per second. And when I'm going to work this thing down, I've got the duration of the ultrasonic pulse as well, and that is 200 microseconds. So I just need to calculate the distance. I'm going to compare it with this value, right? So V is equal to D by T. So yeah, distance should be V times T, right? And I've got the speed, and that comes out to be 4120 times T. The T is 200 times 10 raised to the power of minus 6. And I'm just going to work this thing down, and I must be having something like 4120 times 200 times 10 to the power of minus 6. And when you're going to work this thing down, you must be having something like 40 centimeters, right? So you can see that the transmitted and the reflected wave are going to overlap if the crack is at a distance of 4 centimeters, right? So what we're going to mention, we've got this distance, which is less than 0.04 centimeters, right? Sorry, we've got 40 okay, which is less than the 4 centimeters, right? And if it is less than 4 centimeters, what does that mean? That the crack will not be detected, right? The crack will not be detected. That is what we're going to mention over here, right? And after this thingy, pulses of ultrasound with a higher frequency can be used to find out the cracks of the shorter length. Now you can easily see that if you've got a higher frequency, you should have a lower wavelength. And if you have got the small wavelength that is comparable to the length of the cracks, only that case will be visible, right? Remember that for something to detect, their wavelength should be equal to their, their distance, their interatomic distance. In this case, what you can write, since a higher frequency wave should have a lower wavelength, so it will diffract less, right? It is going to diffract less to give better resolution, right? To give better resolution. Is that clear? So that is what we're going to talk about. Now we have got this question number 14. And in the question number 14, you have got an electric bicycle. The battery contains several identical cells connected in series. Each cell has an EMF of 1.5 volt, and one of those cells is connected over here, and the reading on the voltmeter comes out to be 1.4 volt, right? And we need to calculate the internal resistance of the cell when the resistance of the variable resistor is 10 ohms, right? So first of all, if you've got this 1.4 volts or something like that, I'm going to calculate the current, right? So the current in this circuit has to be something like, since the current is, since V is equals to IR, so I should be equals to V upon R, right? The voltage in the circuit is 1.4, right? Divided by the resistance, which is 10. So the current that I'm going to get is going to be 0.14 volts, right? But now I need to calculate I need to calculate the resistance of the battery itself. So you can see that the internal resistance, remember that the formula for the internal resistance would always be something like the difference in the voltages, the difference in the EMF and the potential difference basically, divided by the total current that is flowing through the battery, and that has to be 0.14. If you could see, the PD in the circuit is 1.4, but the EMF of the battery was 1.5. So the delta V has to be 0.1 divided by 0.14. I'm just going to work this thing down, and I must be having something like 0.71 ohms, right? You have got 0.71 ohms over here. That is going to be the internal resistance. The battery in an electric bicycle gets warm when the battery supplies power to the motor in the bicycle. Explain why the battery gets hot when the bicycle is going up a steep hill. So first of all, if the bicycle is going up the steep hill, what does that mean? That, more work is done by the bicycle at first, right? More work is done by the bicycle. And you know why? Because it is working against the pull of the gravity, right? So more power, if it is doing more work, so more power would be supplied, more power would be supplied. And if you're increasing the power, everybody knows that since P is equal to IV, P is equal to IV, right? So power is directly proportional to current, right? Higher the current, higher the power derived from the battery, the higher would be the current flowing inside the battery. And everybody knows that when the current is going to increase through the battery, the temperature would rise as well, right? The temperature would rise as well. Is that clear? So that is how energy should be transferred as thermal energy due to internal resistance increase, right? That is what we need to know whenever you're talking about it. Okay. After this, we've got this question number 16. The diagram is showing an apparatus used to demonstrate the diffraction of an electron beam in a school laboratory, right? You've got something like that. You've got graphite, you've got the electron beam, you've got the vacuum, you've got the curved fluorescent screen. A beam of electron is accelerated by a high potential difference towards a piece of graphite. The graphite deflects the electron beam, blah, blah, blah. And we need to show what the diffraction is. Remember that, the diffraction is the spreading out of waves whenever it passes through the obstacles, right? Or whenever the light bends itself, whenever it is passing through the obstacles or something like small cracks, that is known as diffraction. Everybody knows that. An electron is accelerated through a potential difference of 4.9 kilovolts, and we need to know that the de Broglie wavelength is about 1.8 times 10 to the power of negative 11. So first of all, I'm gonna get myself, because I need to calculate the de Broglie's wavelength, and de Broglie's wavelength is equals to lambda is equals to h upon p, Planck's constant divided by the momentum. I know the mass of electron, but I do not know the velocity of electron. So first of all, I need to calculate the velocity of electron by keeping that the kinetic energy of the electron would be equal to the work done by the battery on an electron. So I'm going to calculate the velocity, and velocity comes out to be 2VE divided by something like m, right? So V comes out to be the square root of 2VE divided by M. Now I'm going to plug in the values. The voltage is given, that is 4.9 times 10 raised to the power of 3. The charge on an electron is given, and that is 1.6 times 10 raised to the power of negative 19. And mass of the electron is given, and that is 9.1 times 10 raised to the power of negative 31. So I'm just going to work this thing down. I'm going to take the square root, and I'll get myself the final answer. And the speed of the electron is going to be something like 4.15 times 10 raised to the power of 7 meters per second, right? Once I've got the velocity, I'm just going to calculate the wavelength. Planck's constant is 6.63 times 10 raised to the power of negative 34. Since momentum is a product of mass and velocity, the mass is something like 9.1 times 10 raised to the power of negative 31, and the velocity is something like 4.15 times 10 raised to the power of 7. When you're going to work this thing down, the wavelength that you must be having is 1.75 times 10 raised to the power of negative 11 meter, which is almost equal to the given estimate. So that is how we're going to calculate the wavelength. Now, in this question, a student suggests that the beam of electron would produce a diffraction pattern if a diffraction grating with 500 lines per centimeter, right? If a diffraction grating for a lines, 5,000 lines per centimeter. So we just need to get the, D from here, because D is equals to number of lines per meter, right? Deduce whether the second order maximum would be clearly visible on the screen. Well, we can only deduce the second order maximum by the value of theta. And if the diffraction is taking place, the governed equation would be something like n lambda is equals to d sine theta, right? So we have got the wavelength and we've got the n. For example, I'm plugging n is 2 to check out the second order maximum. So 2 times 1.8 times 10 raised to the power of negative 11 equals to, how can I calculate d? 1 upon number of lines, remember that, right? So the number of lines we've got is 5,000, but we need to calculate the number of lines per meter. So that is why I'm going to times it by 10 raised to the power of negative 2, right? And then multiply it by sine theta. So by working this thing down, sine theta would be something like 2 times 5,000 times 1.8 times 10 raised to the power of negative 11 divided by 10 raised to the power of negative 2. Whatever the answer I get, I'm going to calculate the sine inverse, and theta comes out to be 0.00103 degrees, which is quite unrealistic, right? This much small angle theta cannot really be measured. And if this angle cannot be measured, you can just simply say that it would not be clearly visible because the angle is very small, right? So that is somehow we're going to talk about this question. Now we have got this question number 16, and we need to state that what is meant by an EMF of 6 volt. Well, everybody knows that the EMF is the work done on a unit positive charge. So if you have got an EMF of 6 volt, what does that mean? That 6 joules of work is done on each charge of 1 coulomb, right? On each charge of 1 coulomb. Now, in the next part B, the reading on the voltmeter is 1.64 volts. Show that the reading on the M-meter is about 20 milliampere, right? The reading on the M-meter is about 20 milliampere. We need to calculate the current. Since the circuit is in series, the current has to be the same. And if the current has to be the same, we just need to calculate the current. Current is going to be something like I is equals to, since V is equals to IR, so I must be equal to V upon R. Now the thing is that what would be the voltage over here? If you have got something like 6 volt over here and 1.64 over here, okay. The total EMF of the battery is 6 and voltage divided over here is 1.64, right? So in the series voltage changes, if you've got 1.64 over here, the voltage over there must be something like, the voltage in the rest of the circuit would be something like 6 minus 1.64, and that must be something like 4.36. So that is the voltage 4.36, right? And 4.36, we just need to divide it by 4.36, we just need to divide it by the resistance, which is something like 200 over here, right? So I'm just going to divide it down. I'll calculate the resistance. I'll calculate the current over here. And that comes out to be, the current comes out to be 2.18 times 10 raised to the power of negative 2 amperes, which can also be written as that 21 milliampere, which is almost equal to 20 milliamperes, right? Did you get that? So that is how we're going to talk about this question. Determine the resistance of the resistor X. Now we need to calculate the resistance of the resistor X, right? Okay. So since we need to calculate the resistance of the resistor X, first of all, the thing is that we know the total resistance of the circuit? If we have got the total voltage, whatever it is, right? And if we have got the total current, we'll get to know the total thingy as well. Everybody knows that the current in the series is constant. If we have got 21 milliampere over here, that would be the same current passing through this thingy as well. So I'm going to calculate the total resistance of this thingy first of all, right? The voltage is 1.64. So the resistance is going to be 1.64 divided by, I'm talking about the total resistance. And the total current flowing through it is 2.18 times 10 raised to the power of negative 2. And that comes out to be something like 75.23, right? So I've got the total resistance. One of them is 100 ohms. I'm going to use the formula for the parallel combination and I'll get myself X, right? So 1 upon Rx plus 1 upon 100 should be equal to 1 upon 75.23. I'm going to work this thing down. And whatever I'm going to do, I can just simply write it like 1 upon Rx equals to 1 upon 75.23 minus 1 upon 100. You're gonna subtract them up, whatever you've got, get the reciprocal, and after taking the reciprocal, you must be having the total resistance as something like 303.7 ohms, right? So that is how you're going to calculate the total resistance across X. Determine the power dissipated in 100 ohm resistor. So you need to calculate the power dissipation in 100 ohms resistor. So what you've got the resistance and the voltage has to be the same as well. So you can just simply use P is equals to V square upon R. The voltage across that circuit was something like 1.64 square divided by the resistance, that is 100. I'm going to divide them down and I'll be having 2.70 times 10 raised to the power of minus 2 watts. So that is how I can get myself the final power. Now, the student makes the following prediction. If I switch the position of 100 ohm resistor and 200 ohm resistor, then the reading on the voltmeter will increase. Discuss the student prediction. You do not need to include calculations in your answer. So first of all, if you're talking about the circuit, you've got two circuits. One of them is Rx. The other one is something like, you're going to switch them. This should become 200, right? And, both of them are connected to the voltmeter. And then later on, that is connected to the 100 ohm. I've switched that position. And you've got this Rx. So what are you basically doing? You've got Rx that was 303 and then you've got 200. So if you are increasing the resistance over here from 100 to 200 ohms, what does that mean? That the resistance of the parallel combination would simply increase, right? The resistance of this combination would simply increase. And if the resistance of this, of the thingy would increase, what does that mean? That the reading across the voltmeter would increase as well, right? Because V is proportional to R if you're going to keep the current constant. So if you're going to switch them 200 in place of 100, then you'll be having a greater voltage across the voltmeter because V is proportional to the voltage. Now you've got this question number 17, and we've got a vibrating tuning fork is placed near to the open end of the tube that is closed at the other end as shown. You've got the tuning fork and you've got the open-ended tube over here. You're going to vibrate that tuning fork and you must be having some waves, some sound particles, some particles of the sound wave like air particles would be moving inward. At the same time, some of them would be getting reflected and they would be coming back, but some of them would still be moving in, right? And since both of them would be having the same frequency because of the same source of production, they're going to superpose. And superposition, because they're superposing with the same frequency traveling in the opposite direction, they must produce a stationary wave, right? So the basic stationary wave that we can have would be something like this and this, right? This is a basic fundamental wave over here. So I've just told you that how the stationary wave would be produced over here, and the basic fundamental would be something like this. Describe how a stationary wave is formed inside the tube. We need to talk about that, how a stationary wave is formed inside it. The 6-marker question, you need to write every detail. So first of all, just tell them that how the stationary wave or the waves were produced, right? So first of all, vibration, vibration of the tuning fork produces sound wave. That is the first point. You need to know, you need to tell them that from where the sound wave would be producing, right? Sound wave would reflect. I just told you initially, the sound wave would reflect from the closed end. Sound wave would reflect from the closed end, right? It or the reflected sound wave will superpose the still incident sound wave, right? They're going to superpose since both of them would have the same frequency, right? And they are at the same time traveling in the opposite direction, right? They are traveling in the opposite direction. And if they are traveling in the opposite direction, what does that mean? They will give rise to standing or stationary wave, right? They will give rise to standing or stationary waves. Now, since we have got 4 points and we've already explained them, but this is a 6-marker question, you need to add on extra detail. So what you can do, you can write the 5th point as that wherever you'll be having a maximum amplitude would produce anti-naught, right? Maximum amplitude would produce anti-naught. And 6th, minimum amplitude produces knots, right? So that is how you're going to write the 6-marker question down. Remember that for a 6-marker question, you must at least plug in 6 points. Otherwise, you're going to get 4 or 5 in this question. And that is a very critical question as far as those questions are concerned. Those students are concerned, which are going to get A, right? When the length of the tube is 20.4 centimeters, what does that mean? That this is 0.204 meters. The simplest possible stationary waves are formed inside the tube. Simplest possible was the one that I made, something like this, right? With a 1 knot at the closed end and the anti-knot at the open end. This is the one simple basic wave. So calculate the frequency of the sound produced by the tube. So first of all, we're going to get the wavelength. You can see that the length would be L. And if I'm going to write that length in terms of the wavelength, that should come out to be something like, because we've got a distance between an anti-knot and the knot. Remember that the distance between an anti-knot and a knot is the quarter of the wavelength. So the wavelength comes out to be 2L. So I can easily calculate the wavelength, and that's going to be, sorry, not 2L, it has to be 4L now, because 4 going to multiply on both the sides. So 4 times L, and that's going to be something like, 0.204. I'm just going to times them up, and after multiplication, I'll be getting 0.816 meters, right? I've got this wavelength. I can calculate the frequency by using V upon lambda. V is something like 340 divided by the wavelength, that is 0.816. By dividing them up, I'll be having 417 hertz. That is how I'll get the frequency, right? The actual frequency of the sound produced by the tube is slightly less than the calculated value. Because why is that? Because we cannot actually predict that where the anti-naught would be. It must have an ending error. It can end over here, it can end over here, it can end over here, right? So, remember that whenever you're talking about the difference in the actual and the calculated one, the anti-naught is not exactly at the open end of the tube, right? So we can just simply write because anti-naught is not exactly at the open end, right? There is an end correction required in the readings. Now we've got the last question, and that has to be the question number 18. Some types of glue can be hardened to exposure to ultraviolet light. One type of UV lamp contains mercury atoms in an evacuated glass tube. When a large potential difference is applied between the two electrodes in the tube, electrons move between the two electrodes. These electrons collide with a mercury atom in the tube. These mercury atoms then emit photons. Explain why mercury atoms emit photons, right? So we need to talk about this thing. So we need to talk about that, explain why the mercury atoms are going to emit photons. So remember that when you're gonna bombard uh, a, a mercury, you've got this mercury over, the mercury atoms emit photons, right? When you're gonna bombard the mercury atoms with a UV lamp, all the electrons in the mercury atom would get excited, right? And when they're gonna de-excite themselves, they would be emitting photons, right? So first of all, you have excited mercury by bombarding electrons, right? You have excited the mercury by bombarding electrons. So when you have excited the mercury by bombarding electrons, what does that mean? That we have excited the mercury by bombarding electrons. And if you have excited the mercury by bombarding electrons, so the de-excitation, when they're gonna get back to their normal state, the de-excitation would emit electrons, right? So that is how we're going to talk about this question. Now you've got the UV lamp, and for example, somebody is replacing the screen of the mobile phone. You've got the dimension of the mobile phone. You're going to place the mobile phone over here, and you've got the intensity of the light wave incoming, and you've got the time that glue going to take to get hardened. Show that the total energy incident on the glass screen during this time is 130 joules. You just need to calculate the energy. That is very simple. So first of all, you're gonna calculate the power. The power is I times A, right? The intensity is 50 milliwatts per centimeter square multiplied by the area. The area of this thing has to be 7.15 times 14.7, right? You must be, wondering that why I'm not changing the units, because I can see that we've got centimeter per square over here, and I'll get the unit of area as centimeter square as well. So I'll get the final power, and that final power comes out to be something like 5.25 volts, right? You can use the calculator. Once you've got the power, you've already got the time as well. So you just need to calculate the energy. Work done should be P times T, if I'm not wrong. Power is 5.25 times the time, and the time gonna be 25 seconds, right? So that is how I'm gonna calculate the work done. And that work done comes out to be something like 131.3 joules, right? 131.3 joules. So that is how I'll calculate the total energy incident on the glass screen during this time. We've got the option number 2 now. Determine the number of photons incident on the glass screen in this time, right? Determine the number of photons incident on the glass screen in this time. We need to calculate the number of photons. So remember that if you want to calculate the number of photons, you need to divide the total energy by energy of one photon, right? So we've got the total energy that was 131 point something. And now I'm going to calculate the energy of one photon. And energy of the photon can be calculated using E is equals to HF, right? And, E is equals to HC upon lambda as well. H is 6.63 times 10 to the power of negative 34. C is 3 times 10 to the power of 8. and lambda is given 395 times 10 raised to the power of -9. I'm going to sort it down, and I will be having something like 5.03 times 10 raised to the power of -19 joules. So if I'm going to calculate the number of photons, remember that the total energy was 131.3 joules, 131.3. I'm going to just divide it by 5.03 times 10 raised to the power of -19. Is that clear? So you've got this thing. And by dividing them down, I'll have the myself the final number of photons, which would be 2.61 times 10 raised to the power of 20, right? In the C part, the potential difference applied between the electrode in the UV lamp is increased. You are increasing the potential difference. Explain the effect this would have on the frequency of the UV light produced by the lamp. So you can simply see that, if you're providing a higher frequency, E is proportional to F, right? If you're increasing the frequency, the electrons would move to higher energy levels, right? Because they would have enough energy. And when electrons would move to higher energy levels, so, sorry, when you're gonna, sorry, E is also proportional to V as well. When you're gonna apply the voltage, the energy would increases, and the increase in energy would also increase the frequency of the UV light produced by the lamp, right? Because everybody knows that work done is also equals to VE, right? So increasing the voltage would increase the work done on the charges. Charges, if you're going to do more work on the charges, they would move to the higher energy levels. And when they'll de-excite themselves to the lower energy levels, they would emit photons with a higher energy, meaning thereby the higher frequency. So the frequency of the UV light would increase, right? Now suggest why the hardening time of the glue is reduced if the lamp is moved closer to the mobile screen. Well, if the lamp is moved closer to the mobile screen, the intensity would increase, right? You're going to increase the intensity, and increasing the intensity means that the number of photons arriving per second on the screen would increase as well, and that is why the energy transferred per second would increase. And since the energy is increased, it would take less time to get hardened, right? So that is how we're going to do this paper. I've made sure that you guys know how to do a paper with respect to the marking scheme. And if you've got any questions regarding a marking scheme topic, or any from any of these questions, you can just comment in the comment section. Thank you very much.